In our next section, we're going to look at implementing segment routing with OSPF. Specifically, we'll look at the configuration steps, which are not really that involved, and then the verification, which is going to be not necessarily more involved, but we're going to take a look at from the actual data plane point of view, what changes when we're doing LDP versus segment routing, and we'll take a look at that in Wireshark. And you'll see that unless you know what specific label numbers you're looking for, there's no functional difference between the two of them ultimately. Okay, so to configure segment routing with OSPF, there's mainly going to be two minimal steps. Okay, the first is to configure what we call the connected prefix SID map, or essentially the advertisement of your loopback into the segment routing network. Okay, once we do that, then we go under the IGB process and we enable segment routing under there. That's what's going to enable the, actually in this case, not the type length values. This would be the opaque LSAs. But basically it just means that that extra information inside OSPF that we're advertising that's talking about the specific label numbers. Okay, a basic look at the config here. You can see that there's not a ton going on. And so there's a new global mode that is segment routing for MPLS. We go to the connected prefix SID map under address family IP version 4 or IP version 6, depending on which you're using. In this case, we're doing v4. And then in this case, router 1 is advertising its loopback 1111/32, and it says it's using an index value of 1. This means that it's taking the segment routing global block, or the sRGB, which starts at 16,000. It's adding 1 to it, so 16,001. That becomes its node SID, or essentially the global label value that we're advertising into the OSPF network. Okay, for iOS XR, not too much more complicated. We're going to go under the routing process, turn segment routing on. Then under the area, under the interface, specified what the index of the prefix SID is. So in this particular case, if we look back at our diagram, this is going to be on node 11, which is XR1. Okay, so we have nodes 11, 12, and 13, and then nodes 1, 2, and 3 at the bottom. So XR1 is saying my index number is 11, which really means that its global label value is 16,011. Okay, this is the reason why I mentioned that you need to somehow keep track of these numbers, because they're statically defined and they are globally significant. So if somebody else chooses the index number 11, same as XR1, then we're going to have a forwarding problem in the core. Okay, some verifications we're going to go through. Most of these are going to be under show IP OSPF segment routing. And then in the database, we could look at the opaque areas. That's going to show, or the opaque area LSAs, and that's going to show the specific details of what they're actually advertising into OSPF. Okay, in iOS XR, for whatever reason, there's not really many good verifications, at least in the version that I'm running. We can mainly look at just show IP or show OSPF database for the opaque area, and then see what specifically is encoded into the database. Okay, now the other issue that we're potentially going to run into here is how do we integrate segment routing with LDP? So assuming that LDP and segment routing are running at the same time, the issue is that LDP is going to be preferred. So let's say, for example, that we wanted to migrate between the two of them. We're migrating towards segment routing, but right now everyone is running LDP. So what we would do would be to turn segment routing on everywhere. Okay, make sure that OSPF or ISIS is successfully running for segment routing. Under the edge routers, we would configure segment routing MPLS SR prefer. This just means that if you have an LDP label for the destination and a segment routing label, prefer the segment routing label. Okay, once the edge routers are done, then LDP effectively could be removed from the core. Or you could just leave it there in case there's something wrong with segment routing that you don't advertise a prefix that you need, then it's going to be advertised via LDP. Okay, so first let's take a look at what is the current state of the MPLS network. And this topology here is running in viral, so for future reference on this, If you go to the INE-viral GitHub repository, this is going to be under courses and then implementing segment routing on Cisco IOS XR and XE. Okay, we're starting with the base MPLS L3 VPN with OSPF core example. Okay, the goal again is that we're trying to get reachability between router 6 and router 7. These are the end customer routers. Okay, so on router 6 we have a loopback interface that is 6.6.6.6/32. Router 7 we have likewise 7777/32, and then we're trying to hop over the core in order to reach between those two networks. Okay, so on router 6, looks like connectivity is good. And if we do a trace route, we should see that this is using the MPLS label path in the core of the network. Okay, so to simplify this a little bit further, let's take the iOS XR links out to begin with. So on router 4, we're going to shut down gig 2.411. And then on router 7, we're going to shut down gig 2.713. Okay, so temporarily we're going to only have one path to forward through. So on router 4, we'll say on interface gig 2.411 is shut down. And then on router 7, show IP interface brief. Interface gig 2.713 is shut down. Okay, we should still have end-to-end transport between 6 and 7, but we're just going to reroute an alternate path. Okay, so 6 is going to 5, to 1, to 2, to 3, and then to the final destination. Okay, so we only have one current path. Okay, if we take a look at on router 1, and let's show run pipe section LDP, we see that under some other subconfig mode, okay, which in this case is going to be our routing process, we have the MPLS LDP autoconfig command. So if we look at the show MPLS LDP neighbors, we have two neighbors. Okay, we have an adjacency to router 2, we have an adjacency to node 11, okay, which is XR1. And if we look at the show IP route for OSPF, and we compare this to the show MPLS forwarding table, we should see that we have labels for example, the loopback interfaces. Okay, one of the paths it looks like is not running labeling. Okay, so to gig 2.112, so this would be a potential issue if we were actually routing packets out that link. So if we show IP route for 3333, any packet that routes to 12 is going to have an issue right now because it doesn't have a label associated with it. Okay, this probably is some sort of LDP adjacency problem. If we go to XR2 and show MPLS LDP neighbors, looks like LDP is not running. Okay, so that's probably the issue. So let's look at the show run router OSPF. We have MPLS LDP autoconfig on, but why would we not be forming? Oh, probably this. Probably in global config we don't have MPLS LDP. Okay, so let's show MPLS LDP neighbors. Show MPLS LDP interfaces. Says it is enabled via autoconfig. Okay, let me kickstart the process because this router right now we don't actually need it. So let's say commit, confirm, and I want to say 30 seconds to roll back. Commit replace. Okay, so that's going to replace my config. Okay, so right now when we look at the LDP label bindings, okay, we see that we don't have labels for the VPN route, so these are going towards the customer network, but we do have labels for the loopbacks on the other side. Okay, if we look at the show BGP, VPN v4 unicast for all tables, This is really going to be the key determining factor of how we are forwarding traffic over the MPLS core. So from our portion of the network, router 1 is connected towards router 6. We're trying to get towards the core over towards router 7. So notice here that BGP is learning that route 7777, and it says to get there we're going to use the loopback of router 3. So what this now means is that we're going to take whatever label is inside this advertisement from BGP VPN v4. We're going to put that at the bottom of the stack, and then we're going to take whatever label we're using to get towards router 3 and put that on the top of the stack. Okay, so next let's take a packet capture and see what does this result actually look like. So we're going to do the capture on router 2. Okay, so router 2 is going to create a PCAP. Okay, well, actually not router 2 directly. The viral hypervisor is going to do that for us. And this is on this one here, L3 VPN with OSPF. So we want to go to the simulation. We want to go under interfaces, and on router 2 gig 2, I want to create a traffic capture. Okay, so next let's send some packets through. So let's go back to router 6. Let's do a ping to router 7. Let's do a trace route to router 7. Okay, and we're going over the router 2, router 3 path. Okay, so next let's take our PCAP. So if we go down to traffic captures, let's go ahead and download this. Okay, and here's our capture. So we see behind the scenes we're running LDP, we're running OSPF, and then we have BGP. Okay, so BGP port 179. Okay, if we go towards the end, we should see our pings. And actually, let's just sort for this. Let's say ICMP. And we see pings going between 6 and 7. Okay, so based on the VLAN ID, we can tell where specifically in the network was this captured. So if we go back to the diagram, the first link from 6 to 7 should be, from router 2's point of view, this is VLAN 12. Okay, so it was coming in this interface from router 1. It came in and it had two labels, label number 17 on the top and label number 18 on the bottom. Okay, next we switch it to the outgoing interface. We switch it to port 23, and we remove one of the labels. So previously there were two labels, 17 and 18. We're popping the top label and then forwarding it towards router 3. Okay, so specifically this was, again, 17, 18, and then we popped the top label and it was just 18 towards router 3. So specifically what this means is that 17 should be our LDP transport label, and number 18 is our BGP VPN v4 label. Okay, to verify this, we could go to router 1, and let's look at the show MPLS forwarding table. And we want to know what's the label to get to the exit point, which is router 3. Show MPLS forwarding table. And it says we're using label number 17 in order to get to 3333. Okay, so 17. And then we look at the BGP label. So if we look at show BGP, VPN v4, unicast for all tables, we want to know the prefix 7777/32, and this has label number 18. Okay, so just like we saw from the capture, 18 was the BGP VPN version 4 label, and then number 17 was the LDP transport label. Okay, let me see real quick before we go any further. Let's say show MPLS LDP interfaces. LDP, or just show MPLS interfaces. I'm wondering why is it not forming. let's see, show IP route 12, 12, 12, 12. Oh, that's what the issue is. It's missing, we're missing the advertisement for the loopback. So let's say show run router OSPF. I forgot to put the loopback here. That's what the problem is. So router OSPF1, area 0, interface loopback 0. Okay, let's see if I did the same thing on the other boxes. So on XR3, let's show run router OSPF. And same thing, I'm missing the loopback. Okay, the loopback is needed for LDP because of the TCP transport. So the hello message goes out the physical interface coming from the IP address on that port, but in that hello message, we specify what our transport address is. Transport address by default is loopback 0. So effectively what's happening is that they're receiving the LDP hellos, but then they're trying to form a unicast TCP session, but they're unable to do that because I didn't advertise the loopback into OSPF. Okay, so a very typical troubleshooting case you would see with MPLS. Fix is just to advertise interface loopback 0. Okay, let's make sure XR1 has that show run router OSPF, which it already does. Okay, so now from router 1, we should see now BGP comes up, and we should see hopefully that LDP comes up. Show MPLS LDP neighbors. Okay, which it is. Okay, so let's look at the full show run, and I want to see, do these boxes have the, yes they do. Okay, so when we looked at the labels that were in the current table, this is with LDP. This command here, MPLS LDP label, allocate global host routes, this is what makes regular LDP perform more like segment routing, because we're only advertising a binding for the loopback. So I'm actually going to take this out just to show what the default behavior is, and then we'll look at the difference here with segment routing. So no allocate global host routes. That's on routers 1, 2, and 3. And then let's show MPLS forwarding table. Okay, so let's see what else has a label here, which is these. Okay, so now notice we have all of these /24s that are the transit networks. Now again, the issue is that from the end customer point of view, they're never sending traffic to the link. They're only sending packets through the link. So the only real label that we need is the /32 loopback of the provider edge. We don't necessarily need the route reflector in the middle. We don't necessarily need any of the transit links. But this is going to be an optimization of segment routing, just that it behaves like this by default. So you could get LDP to do this. Again, it's just that it's not the default behavior. It's going to advertise whatever routes you have in OSPF or ISIS. Those are going to get advertised with labels on a one-to-one basis. Okay, so next step, we're just going to turn LDP off. Okay, so in the case of regular iOS, we're going to go under router OSPF1 and say no MPLS LDP auto config. Okay, let's say show run include MPLS. Actually, it's all one word. No MPLS LDP auto config. Okay, additionally, let's go to router 6 and let's leave this ping running. And what we should see, the result of this is that as soon as we turn LDP off, we will no longer have connectivity. Because the big issue is that these final destinations, 6666 and 7777, the devices in the middle of the core, okay, like XR2, they don't know these destinations. So if we show IP route 6666, doesn't have it. Okay, the only thing that XR2 knows is that if a packet comes in and it has label number 17, then I need to forward it in this particular direction. Okay, it doesn't know anything about the underlying VPN labels, like number 18. Only the provider edge devices are going to have that intelligence. Okay, the only thing the P router needs to do is just swap the labels as they're coming between the interfaces. Okay, so on router 1, turn LDP off. Same thing on router 2. And router 3. Okay, for the XR boxes, let's look at the show run router OSPF. This is the same thing. So under, we're going to go to global config, router OSPF 1, no MPLS LDP auto config, and then commit. Okay, so this is on XR1, 2, and 3. Okay, the end result hopefully should be that router 6 no longer has connectivity, okay, which is the case. Okay, we'll see that they will still learn the routes though. So if we go back to router 1 and we look at the BGP table, nothing is going to be changed here. So if we show BGP, VPN, v4, unicast, all, we still know how to reach 7777. The issue is the transport label to 3333 is broken. And we can see this if we do a trace route within the core, trace to 3333, source 1111, it's no longer following an MPLS labeled path.